Welcome back, my dear student. You know we are in a journey of learning some chemistry focusing basically on MAKAUT syllabus or AICT syllabus. And during our journey, although our most aim is a final exam, but still we will learn some basic chemistry during this discussion. Okay. So today my topic is particle in one dimension. In one lecture, it will not be sufficient to cover the whole things. So we need 3 or 4 lectures to complete the whole thing of the particle in one dimension, which are included in our syllabus. And I am Dr. K.S., that is Dr. Knowledge Seeker. But before going into the details of the application of Schrodinger equation for particle in one dimension, let us discuss a simple conjugated organic molecule, that is 1,3-butadiene. Okay. Just 1 minute. Oh yes, it is working. Okay. So where is it? Just 1 minute. Let me allow to open the whiteboard. Okay, just wait. So we are actually today discussed that I have already told you that particle in one dimensional box. Okay, but if I start abruptly, particularly you will learn nothing. So step by step we will follow all the things which are included in the particle in one dimensional box. Okay, it is taking time, just wait for some time. Okay, so dear friends, so my dear students, so I talked about a particular simple conjugated system, that is 1,3-butadiene. 1,3-butadiene molecule. What will be its structure? Structure will be H2C double bond, CH single bond, CH double bond, CH2. This is 1,3-butadiene. Now here 2 pi bonds are there, and each carbon atom is contributing 1 electron to the formation of those 2 pi orbital. So let's try to figure it out. It can also be written in this way, that is a carbon atom and a p unhybridized p orbital is there on the plane of the sp2 plane of the carbon atom. So here CH, another p orbital will be there, and here also the same case, another p orbital is there, and here again there will be a unhybridized p orbital, and this is how the different p orbitals are located on each carbon atom. Now actually these 4 electrons are completely delocalized in these 4 p orbitals. Now if you focus particularly on one electron, say you have just considered the electron associated with this carbon, say its position is here. Okay, now what will be the value of the potential energy? Now the potential energy can be given by the equation K potential energy, that is V, is equal to K Q1 Q2 by R, where K is called the Coulomb constant. Okay, so potential energy is depend upon R, and it also depends upon the charge. Now this Coulomb constant is also given by 1 by 4 pi epsilon. I think you all know these things from your higher secondary classes. So this is actually the potential energy. Now I am considering several position of the electron in the vicinity of the carbon, say here, etc. Okay, so just assume firstly the electron was here, and then it has moved to that position, and that particular electron has moved to that position and to that position, and finally here, and it will actually delocalize through the all different carbon atoms p orbitals. Okay, so I am talking only about one electron, not 5 electrons. It has migrated from here to there and there, so on. Okay, now let's consider what will be the fate of the potential energy if it located in different positions. So since R is in the denominator, then what will happen? And if you apply this equation to the nuclear charge as well as charge of the electrons, so the equation will be reduced to k, or 1 by 4 pi epsilon, you can write in this way also, say plus Jd, that is the nuclear charge, into minus E by R, by R. So it will be come out as minus of Z E square by R. So there is a minus sign here. So if R be greater, then what will happen? These numerical value, the whole numerical value will be less, and since there is a minus sign here, actually with increase in distance, the potential energy will also increase, and with decrease in distance of the electron from the nucleus, the potential energy will drop. So if we like to plot this, what will happen? You will get a curve like this. Okay, say here is the this is the potential energy at this position. So with decrease in the distance of the electron from the nucleus, the potential energy will go on decreasing. Okay, now after that it will lead to a minima when the position is the minima. After that, during the process of delocalization, when it will go out from the influence of that particular shape of that particular carbon nucleus, then what will happen? Again its value will begin to increase, and so on. Okay, now the same thing will happen for the second carbon atom, this carbon atom, same thing will happen. So again we will get a curve like this. Similarly for the third carbon atom and fourth carbon atom. Okay, now if you just consider one particular carbon atom and the nucleus, one particular carbon atom and the electron, the situation will be something like this. Okay, now if we simplify or extend this into a model, then we can say, we can draw the model like this. In this region, the potential energy in this region, the potential energy is low, and outside this region, abruptly the potential has become higher. You can also you can think this thing in this way, that if there occurs same charge, like same sign of charge, again the potential energy, for example, if a particular charge particle is being attracted or repelled by some other charge particles, say both has the same sign, then there will be a high increase of the value of the potential energy. Because of the same sign, all will be positive. Okay, and that particular charge will be repelled by the another charge. So we are considering, so high potential means there is a chance of, of course that particular particle will be repelled. Now we are considering in a system like this, where the potential energy outside this region, this is a well like things, that is well in Bengali it is called কুয়ো, জলের কুয়া. সো পার্টিকেলটা ঠিক এইরকম দেখতে, আর পার্টিকেলটা এর ভেতরে যদি কোনো পার্টিকেল থাকে, সে এখানে এর ভেতরে একটা পার্টিকেল আছে, ওয়ান পার্টিকেল অনলি. ওকে, this particle moving here to there. So if in the outside region the potential be very high, say it is high such that it is V infinity, and it is in the outside the potential energy is V infinity. So obviously the particle will be repelled and will be forced to go to and fro in this particular region. It will go forward and will again come back, go forward and again will come back. So it will be trapped in this region, this particular particle. And for our convenience, we can assume that the potential energy inside this well is 0, that is V is equal to 0. Of course there will have some potential energy, but that will maintain a constancy, and for our convenience we have considered this potential energy will be as 0, and outside this region the potential energy is very very high, and V infinity is the potential energy. Okay, and that is the reason the particle will move only back and forth here and there. Okay, so this is the concept of particle in one dimensional box. The particle is moving in one direction, say in the x direction, and it is remaining trapped in this particular region. This is what is called the particle in one dimension problem. And you see, this type of problem can be applied to this type of system where conjugated bonds are present. Okay, we can use this model as well to calculate the energy and other things. Okay, now let's see this animation. Actually, what happens in the, just wait for 1 minute. What happens in the how is looking actually particle in one dimensional box? I have just created this animation with the help of Wikipedia, and you see the particle, what will be the fate of the particle? The particle will be moving in this way. It will go forward and will again come back to the backward direction, and it will remain trapped in these two region and moving in a particular axis. Say for our convenience we are talking this axis as S axis, and this particular problem is called the particle in one dimensional box. I think I have been able to make you clear all the things. Okay, now again come to our problem. So this is the particle in one dimensional box. I am clearing whole canvas. It is not working, I don't know why. Okay, it will take some time. Okay, so let's start with a fresh. So this is actually the potential well. Okay, as if the particle has been trapped in this well. Okay, now outside this particular well, V is very high, and we have told that it is infinitely high, and as a result the particle will be trapped inside this region, and here the potential energy will be low and constant, will maintain a constancy, and for our convenience we have assumed that potential should be 0. Now we have learned Schrodinger equation, and there are many applications of the Schrodinger equation. You can apply to many systems, and you can find out some valuable parameter, some you can valuable conclusion by solving Schrodinger equation. And although there are many types of problem where we can apply the Schrodinger equation, for example simple harmonic motion, hydrogen atom, and in some simple molecules also, but here we are discussing the most simplest application of the Schrodinger equation, that is particle in one dimensional box. Now our target is to make a Schrodinger equation for which will fit this particular problem. Okay, in general we know Schrodinger equation is H psi is equal to E psi. This is the Schrodinger equation in general, and you know, so we are now trying to form a Schrodinger equation for this particular problem, that is the problem of particle in one dimensional box. Okay, I am telling again and again same things, please do not feel bored. Okay, actually it is required to tell some things repeatedly so that you can grab all these things. Okay, now so H psi is equal to E psi is the Schrodinger equation, where H is the, you know, Hamiltonian operator. Okay, so if you put Hamiltonian operator means it is the operator for the total energy of the system. Now Hamiltonian for this particular system will be given by minus H cross square by 2m del squared plus V psi. This is the Hamiltonian. Okay, this is the Hamiltonian for any system. It is general, very general, and we will reduce these things actually it will be fit for the particle in one dimension. This is the general equation. It can be applied to any system. Okay, so this whole thing is H psi is equal to E psi. Okay, now since we are considering, so this is again Laplacian operators, and del squared means actually del 2 by del x2 plus del 2 by del y2 plus del 2 by del z2. But for particle in one dimension we will consider only x direction, so no value of y or z, we will only focus on the x direction. So the Laplacian operator will be reduced to d by d2 by dx2. Not partial sign will be there because we are considering only one variable, not more than one variable. So this is, now you have to consider again another thing, that H cross is called the reduced Planck constant. Reduced Planck constant, where H cross has the value is equal to H by 2 pi. So the equation can be reduced. So H square, of course, H cross square will be equal to H square by 4 pi square. Now if you put this value of H cross square here, if you put the value of H cross square to here, the Schrodinger equation, and if you put del squared as d2 by dx2, the whole equation will be reduced to, I have written here, that is minus H square by 4 pi square into 2m. 2m is there, just note it down, d2 by dx2, okay, plus V is equal to 0, because we have considered for your convenience that the potential energy inside the box is 0. So it will be equal to E psi. Clear? Now if we, so there will be psi also here. So if we simplify this equation, what will happen? If we simplify this equation, the equation will ultimately, you will try by your own, ultimately the equation will be reduced to minus H square by 8 pi square m. So instead of del square, now we will write d2 by dx2, outside there will be psi, will be equal to E psi, and so ultimately the equation has been reduced to minus H square d2 psi by dx2, here there will be 8 pi square m. So this is the equation, it will be equal to E psi. Now if you rearrange this equation, so d2 psi by dx2 will be equal to minus 8 pi square m by h will be there, h square equal to h square into E psi. So you see, the ultimately the equation, Schrodinger equation, has been reduced to this form. Schrodinger equation has been reduced to this form. This form is called the Schrodinger equation for the particle in one dimension. Now it is a very simple differential equation, and we can solve that, and after solving this Schrodinger equation for particle in one dimension, we will be able to find out what is the value of psi. And there are some postulates of quantum mechanics. Since I am not going into the detail of all the things which are included in quantum mechanics, but basically I am focusing your syllabus, so I have not talked about those things. There are some basic postulates. Actually, people say 5 postulates are there for quantum mechanics, and the first one is something like this, that every microsystem can be analyzed with the help of a state function which is called psi. From psi, every microsystem can be described. Okay, and again there is a postulate. Second postulate is there, that to every observable there occurs an operator, and with the help of the operator you can find out the value of that particular observable. Observable means the parameter that can be measured experimentally. Okay. Now, if you know the psi, okay, then we can apply different kind of operator on psi to get the information about different physical property. For example, if you like to know the momentum of a particle in a particular system, you will be able to find out if you operate that particular operator which corresponds to the momentum, and if you apply that operator, ultimately you will be able to find out the momentum. Again, you will be able to find out the position, and similarly kinetic energy, potential energy, etc. And one particular operator is known to us which is called the Hamiltonian operator. If you apply Hamiltonian operator on psi, you will get the total energy of the system. So this psi is very, very important, and every information about the system can be derived with the help of the psi. So in each case, if you apply Schrodinger equation to any system, your target will be to at first to form the Schrodinger equation for that particular system, and then your target will be to solve the Schrodinger equation for the particular system, so that you can get the value of the psi. And if you get psi, you will be able to know every information about that particular system. And now we are actually learning that what type of the information can we get by from psi by solving the equation for the case of particle in one dimension. Okay. In the next class, we will actually discuss the solution of the Schrodinger equation, and then we will try to find out different type of informations that can be available from the psi. Okay. And after that, the discussion of the quantum mechanics will be concluded as per your syllabus. You know, it is a huge topic, quantum mechanics, and it is really, really very interesting. But you know, our syllabus restricted us to discuss more things. We have to learn many things. Okay, we'll learn one by one. And after that, thank you for listening, and bye bye.